In this video, we'll look at infrared spectroscopy in broad brushstrokes, the essence of which is the study of molecular vibrational motion. This includes motions like the jiggling back and forth of the atoms within a bond, or in a system of three atoms, the wagging back and forth of two atoms connected to a common central atom. These types of motions are easily excited by infrared or IR light, and for this reason, organic molecules absorb infrared light strongly. The frequency response of an organic molecule to applied infrared light is its infrared spectrum. The diagnostic power of infrared spectroscopy comes from the fact that typical bonds like CH, CC, and CO vibrate with characteristic frequencies. Things aren't exact since subtle details of molecular structure do affect vibrational frequencies, but we can look at regions of the IR spectrum to identify different types of bonds within organic molecules. And there's a difference between single, double, and triple bonds for example, CC and CO. Each of the peaks that you see in this infrared spectrum comes from some kind of vibrational motion in the molecule. So for example, the vibrations of the OH bond are associated with this broad peak at around 3,400 per centimeter. Vibrations of the carbon-oxygen bond are associated with this peak around 1100, and at a somewhat higher frequency we find vibrations of the carbon-carbon bonds. Why do the frequencies of bond stretching vibrations increase in the order CO to CC to OH? What exactly do we mean by wave number, and how does that relate to frequency? How do double and triple bonds play into infrared spectra in molecules that contain those structural features? To answer these questions, we're going to develop a relatively simple model of a chemical bond as a spring connecting two atoms, where the important parameters of the model include the masses of the atoms involved. Here the masses are just the atomic masses that we can get off the periodic table, and the intrinsic strength of the bond, which is modeled in this classical picture using a force constant K. We'll look at this model in detail in the next video. And the reason this model is useful is because it allows us to deduce trends in vibrational frequencies as the masses of the atoms involved change and as the intrinsic strength of the bond changes. And so our goal here isn't really quantitative. It's to develop qualitative trends so that we can compare different types of bonds, different types of functional groups, and deduce which one will have, for example, a higher or a lower vibrational frequency.